Hi everyone, I'm Xinghu from University of Toronto. My talk is about register linearizability and termination. This is a collaborative work with Vassos Hatzilakos and Sam Twigg. From seminal work by Golub et al., we know that a randomized algorithm can lose some properties if the atomic objects that it uses are replaced with linearizable ones. I will first show that randomized algorithms may actually lose the important property of termination. I will then briefly recall results by Golub et al. About strong linearizability, namely that strong linearizability preserves all properties, including termination. But unfortunately, it is not always achievable. In particular, multi-writer multi-reader registers cannot be implemented from single-writer multi-reader registers in a strongly linearizable way. This motivates us to introduce the concept of write-strong linearizability for a register, which is an intermediate notion of object implementation requirements that is strictly stronger than linearizability, but weaker than strong linearizability. It may be sufficient to retain the termination property of some randomized algorithms that fail to terminate when the atomic registers that they use are replaced with only linearizable ones. In contrast to strong linearizability, write-strong linearizable registers are implementable from SWMR registers. Now I will get into the first part. In Stock 11, Golub et al. Showed that a randomized algorithm that works with atomic objects may lose some of its properties when the objects it uses are replaced with linearizable implementations. For example, a strong adversary can take advantage of the unatomicity of objects to skew the expected value of a variable. But randomization is often used to achieve termination. So the question is whether a randomized algorithm can lose termination. We show that the answer is yes. In fact, we give an algorithm A such that with atomic registers, A terminates with probability 1. With linearizable registers, a strong adversary can prevent A's termination. I will now describe a toy algorithm to demonstrate the main idea. This algorithm uses an unbounded number of registers, but the one in our paper uses only 3 bounded registers. Think of this toy algorithm as a game involving 3 players, P0, P1, and P2. The game proceeds in a sequence of rounds. During round J, the player uses a MWMR register RJ and a SWMR register CJ. Player 1 writes 1 into RJ. Player 0 writes 0 into R for round J, and then it tosses a coin and writes the outcome in CJ. Then these 2 players go to the next round. Player 2 reads RJ twice and then reads CJ once. If the first value that he reads from RJ is equal to the outcome of the coin toss and the second value is the opposite, then player 2 goes on to the next round. Otherwise, player 2 stops. I will first show that if the registers are atomic, then player 2 holds with probability 1, which is the game terminates with probability 1. Then I will show that if the registers are linearizable, a strong adversary can schedule the operations on those registers so as to keep player 2 in the game forever. Let's first assume that the registers are atomic. If the write of 1 by P1 is before the write of 0 by P0, then player P2 cannot first read 0 and then 1. So if the later the coin toss is 0, P2 holds and the game ends. If the write of 1 by P1 is not before the write of 0 by P0, then player P2 cannot first read 1 and then 0. So if later the coin toss is 1, P2 holds and the game ends. So in each round, the game ends with probability half, and therefore the game terminates with probability 1. The key reason for termination is that since the register R is atomic, the order of the writes of 0 and 1 by P0 and P1 is determined before P0 flips a coin. But now I'll show that if the register R is not atomic, and so each operation is not instantaneous but spans an interval of time, then a strong adversary can prevent termination by scheduling those two writes to be concurrent and setting their linearization order after seeing P0's coin flip. The adversary schedules the operations as follows. P0 writes 0 into the register R of round J. At the same time, P1 starts writing 1 into R, and P2 starts its first read of R. While the operation by P1 and P2 are still ongoing, P0 flips a coin and writes the outcome into the register C of round J. The adversary now continues the execution depending on the coin flip result. If the coin flip is 0, the adversary linear writes the write by P1 after the write by P0, and linear write the first read by P2 between those two writes. And so, P2 gets U1 is 0 for the first read. Then the adversary makes P2 reads R again after the write of P1, and so it gets U2 equals 1. P2 now reads the coin flip value 0 into C. So P2 now has U1 equals 1, U2 equals 1, and C equals 0. This satisfies the condition for staying in the game, so P2 continues to next round. If the coin flip result is 1, the adversary linear writes the two writes in the opposite way to ensure that P2 gets U1 equals 1, U2 equals 0, and C equals 1, which also satisfies the condition to stay in the game. So regardless of the coin flip outcome in each round, by using the above strategy, a strong adversary can ensure that P2 never stops, and so the game does not terminate. So we have the theorem. With linearizable registers, a strong adversary can ensure that the toy algorithm never terminates. This result seems very limited because our toy algorithm does not solve any problem, but it is easy to use it to show the following corollary, which essentially say that for any task solvable by randomized algorithms, including consensus, there are algorithms that exhibit the same problem. They terminate with atomic registers, but fail to do so with linearizable registers. We just show some limitation of linearizability for randomized algorithms, and we will now discuss some possible solutions. Since linearizability is weaker than atomicity, Golab et al. Propose strong linearizability, which is as good as atomicity in the following sense. Replacing atomic objects with strongly linearizable implementations preserves all the probabilistic properties of randomized algorithms. So, what is strong linearizability? Intuitively, with linearizability, operations can be linearized offline. With strong linearizability, operations must be linearized online. With linearizability, we get to decide the order of operations after the fact in view of the entire execution. So, for example, we might linearize O2 before O1 or after O1. Suppose the object is a register initialized to 0, and O1 is the write one, and O2 is a read. If the read returns 0, we must linearize it before the write. But if the read returns 1, we must linearize it after the write. This ability to decide the linearization order offline is useful. At the time O1 finishes, O2 is still ongoing, and whether it returns 0 or 1 may depend on things that happens afterwards. So we can't determine its linearization order yet. In contrast, with a strongly linearizable implementation, by the time O1 ends, It must decide whether the operation O2, which is still ongoing, is linearized before or after O1. And this decision cannot be changed in the future, no matter what O2 does later. That's why strongly linearizable implementation can be hard to achieve. In fact, it is not always achievable. In particular, there are no strongly linearizable implementation of MWMR registers from SWMR registers. There are no strongly linearizable implementations of SWMR registers in asynchronous message passing systems. So the well-known ABD algorithm is not strongly linearizable. This means we cannot automatically transform an arbitrary randomized shared memory algorithm into one that works in message passing system. So we propose a weaker version of register linearizability, which is write-strong linearizability for registers. Write-strong linearizability is an intermediate notion of linearizability. It is strictly stronger than linearizability and strictly weaker than strong linearizability. It is strong enough to preserve the termination of some randomized algorithm that fail to terminate with linearizability, and weak enough to be implementable in some cases where strong linearizability is not. In fact, we give a strongly linearizable implementation of MWMR registers from SWMR registers. Also, we show there is a strongly linearizable implementation of SWMR registers in asynchronous message passing systems. The ABD implementation is strongly linearizable. So, what is strong linearizability? Intuitively, with strong linearizability, both reads and writes must be linearized online. With strong linearizability, only writes must be linearized online. Reads can be linearized offline. For example, consider an execution of a register implementation. P0 and P1 both write to the implemented register, and P2 reads the register. When P0 completes its write, the write by P1 and the read by P2 are still ongoing. If the register implementation is strongly linearizable, then without seeing the complete history, we must decide whether P1's write is linearized before or after P0's write. And this decision cannot be changed in the future. For example, here, P1's write is linearized before P0's write. In contrast, we can decide where to linearize the read by P2 later, after seeing the complete history. For example, it can be linearized before or after the write of P0. Recall the toy algorithm with atomic registers terminates because with such registers, the order of the write of 0 and 1 by P0 and P1 is determined before P0 flips a coin. As we just saw, strongly linearizable registers also ensure this. So the toy algorithm with strongly linearizable registers also terminates. Recalling the toy algorithm, P1 writes 1 and P0 writes 0 and then flips a coin. If the write of 1 is linearized before the write of 0, the player P2 cannot read 0 and then 1. So if the coin turns out to be 0, the player P2 holds and the game terminates. Symmetrically, if the write of 1 is linearized not before the write of 0, and the coin toss is 1, then player P2 also holds. I will now show how to implement a strong linearizable MWMR registers from SWMR registers. Let's first try to do it with the Lamport clock. Each process PI has a SWMR register val I, which contains the latest value that PI wrote timestamped with the Lamport clock. To write a new value V, process PJ reads all the SWMR registers and increments its Lamport clock according to the timestamp it reads. PJ then writes a value V timestamped with the new value of its Lamport clock into its register val J. To read the implemented register, PK simply reads every SWMR register and returns the value with the largest timestamp. We show that this gives the linearizable MWMR register. But unfortunately, it is not a strongly linearizable one. In our second attempt, we replace Lamport clock with vector clock. The timestamps are now vector of size m. Intuitively, the ith component of PJ's vector timestamp is the number of writes by process PI that PJ is aware of. So, is this implementation strongly linearizable? To try to answer this question, let's consider the following scenario. At time t, the write W1 is complete with timestamp 10, but the write W2 is still ongoing and its timestamp is still being computed. It may be only partially formed with just a few entries set. It is possible that P2 reads P1's register before P1 writes to it, so does not see the writes of P1. And so P2 ends up being timestamped with 01, which is smaller than the timestamp of W1. But it is also possible that P2 sees the write of P1, and W2 ends up with a timestamp 11, which is larger than the timestamp of W1. So it is not clear that we can use these timestamps to decide online at time t, whether W2 is going to be linearized before or after W1, as strong linearizability requires. It turns out that we can indeed do it, even though W2's timestamp is only partially formed at time t. In this paper, we show that we can always determine the linearization order of concurrent writes, and do it online by looking at timestamps that may be only partially formed. This is not easy to see, and we invite you to read the paper for details. Regarding implementing a SWMR register in message passing, recall that strong linearizability is impossible, but strong linearizability is possible. In fact, the ABD linearizable implementation of SWMR registers is strongly linearizable. This is because, as we show in the paper, every linearizable implementation of a SWMR register, including the ABD implementation, is strongly linearizable. As we have seen, this is not true for MWMR registers. Lamport clock implementation of MWMR registers is not strongly linearizable, even though it is linearizable. An important remark is now in order. Recall in our toy algorithm, the adversary can prevent termination by linearizing the operations on a MWMR register after seeing the result of the coin toss. You may wonder, is there an actual linearizable implementation of MWMR registers that allows the adversary to do so? The answer is yes. With Lamport clock implementation of MWMR registers and a variant of our toy algorithm, a strong adversary can indeed schedule the steps of the implementation to achieve the linearization order that prevents termination for each possible outcome of the coin toss. For the future work, we can generalize this notion of linearizability to objects other than register and other type of operations. Intuitively, with X strong linearizability, only operations of type X must be linearized online. All other operations can be linearized offline. But it is not clear yet where such generalization would be useful. Another open question is that what type of linearizability is sufficient for the termination of each of the existing randomized algorithms? Some do not even need linearizability. For example, we recently showed that a randomized consensus algorithm by Aspinall and Hurley, which was developed to use atomic registers, actually work even with regular registers. This is all of my talk. Thank you for listening.